single-phase electrical generator. The single-phase generator is composed of two major components, the exciter and a stator. The exciter is an electromagnet that rotates about its axis. The stator is constructed from two electromagnets, or poles, wired in series with a load, and as the name implies, remain stationary. When a DC current flows through the windings of the exciter, a magnetic field is formed. As the exciter rotates about its axis, its field will cut through the windings of the stator, inducing a voltage in the stator. Let's plot a graph of the voltage induced in the stator windings on the y-axis against time on the x-axis as the exciter rotates through one revolution. We will use the north pole of the exciter as a reference. As DC current flows through the exciter's windings, a field is formed. As the exciter rotates counterclockwise from position 1 to position 2, the stator poles offer a lower resistance path for the exciter flux. As the exciter moves closer to the stator poles, more and more of the exciter's lines of flux will tend to flow through the lower resistance path of the stator poles. As the number of lines of flux increase, a higher and higher voltage, and hence current, is induced in the stator. The two stator windings are connected in series such that voltage induced in each of their windings add together and appear across the load. At position 2, the maximum number of lines of flux from the exciter's field are cutting the stator windings, corresponding to a peak in the voltage induced in the stator. As the north pole of the exciter continues to rotate towards position 3, we can see that the number of lines of exciter flux that flow through the stator poles is decreasing, resulting in a reduction in induced voltage. Once the exciter has reached position 3, no lines of exciter flux are flowing through the stator poles. The result is no induced voltage in the stator windings. As the exciter continues to rotate towards position 4, the number of lines of flux from the exciter's field flowing through the stator poles is again increasing. But because the flux is traveling in the reverse direction, the induced voltage is of the opposite polarity as was induced earlier. The peak of this negative voltage corresponds to the exciter's north pole's alignment with the stator pole at position 4 and its corresponding south pole's alignment at position 2. As the exciter rotates from position 4 back to position 1, completing the rotation, the number of lines of exciter flux flowing through the poles is again decreasing from a maximum to 0. We observe that the induced voltage again ramps down from a maximum to 0, completing one cycle of the waveform. One rotation of the exciter through 360 degrees produces one cycle of voltage that alternates polarity and hence current flow. This is referred to as alternating current, which is abbreviated as AC. We can now determine the output voltage at any given point in time along the sine wave by using the following process. To better understand this method, the voltage magnitude at a specific time of the sine wave will be plotted on this XY graph. As the output voltage changes, the voltage drawn on the graph will also change. Once the graph reaches 90 degrees, we can see that a maximum voltage is being output. This can also be set at 270 degrees. At the 180 and 0 degree points, the voltage output will be at its minimum. The generator is constructed such that the output voltage waveform is a perfect sine wave. We can therefore use the sine function to calculate the instantaneous output voltage, shown as VI at any given angle, shown as theta. VI equals V peak sine theta, where V peak is the peak output voltage. For example, to calculate the amplitude of a waveform having a peak output of 100 volts at an angle of 45 degrees, we would plug the values into the equation as follows. VI equals V peak sine theta. VI equals 100 sine 45 degrees. VI equals 70.71 volts. Therefore, at an angle of 45 degrees, this waveform would have an output of 70.71 volts. Magnitude, peak, and RMS. Most voltmeters measure voltage in RMS. The RMS value of a sine wave can be calculated by multiplying the peak voltage magnitude of the AC waveform by 1 divided by the root of 2. The resultant of this calculation is called the RMS value of the AC voltage. Peak value equals the square root of 2V RMS. The RMS value of an AC waveform, when applied to a purely resistive load, will raise the temperature of that load to the same temperature as would a DC voltage of the same magnitude. This means that a 141 volt peak AC sine wave has the same heating effect on a pure resistive load as would 100 volts DC. Frequency. Frequency is the rate at which the waveform is repeated. Hertz is the engineering unit that quantifies frequency and is equal to the number of times a waveform repeats itself per second. For example, a waveform that repeats itself every second is said to have a frequency of 1 Hertz, while a waveform that repeats itself 60 times a second has a frequency of 60 Hertz. In order for our generators to produce 1 cycle of AC, the exciter must complete 1 revolution. This means our generator's exciter must complete 60 revolutions in a second to produce power at a frequency of 60 Hertz. This may seem very high, but this is a common speed for large utility-class steam turbine-driven generators. Period. As stated earlier, to generate 1 cycle of alternating current, the exciter of our generator must complete 1 revolution. The time taken for the resulting waveform to go through 1 complete cycle is referred to as the period of a waveform. The symbol for period is capital T and is equal to 1 second divided by the frequency. For example, the period of a 60 Hz waveform is 1 divided by 60, which is equal to 16.67 thousandths of a second, or 16.67 milliseconds. Time, phase, and degrees. Let's look at a sine wave with a frequency of 60 Hz. The period would be equal to 1 second divided by 60, which would equal 16.67 milliseconds as stated earlier. The period corresponds to the time it takes the waveform to go through 360 degrees. Let's fill in a table that displays the angle of a sine wave and the associated time to reach that angle using the formula time equals the phase angle divided by 360 times the period. If we have 2 waveforms of the same frequency that at any point in time are at the same point in their cycle, they are said to be in phase with each other. For example, if both waveforms reach their peak amplitudes or zero crossing at the same time, they could be described as being in phase with each other. We observed that by taking the peak of the waveform and the sine of the angle of the waveform at the same moment in time and multiplying them, we could calculate the instantaneous amplitude of the waveform. Therefore, these 2 waveforms could also be described as having a 0-degree phase shift with respect to each other, or there is no time delay between each waveform reaching the same point in their cycle. Note that we can only describe the phase shift between waveforms of the same frequency. Let's examine this further. If it were said that waveform 1 were leading waveform 2 by 90 degrees, we could graphically represent this relationship as waveform 1 having reached its positive peak amplitude, while at that same moment in time, waveform 2 would be at its zero crossing just before its positive slope. If both waveforms remain at the same frequency, the phase shift between them will remain constant. Another way of describing the relationship between these 2 waveforms is to state that waveform 1 is leading waveform 2 by 1/4 of a cycle, since 90 degrees is 1/4 of 360 degrees, which represents 1 complete cycle. A phasor or a phasor diagram are ways of representing the relationship between 2 sine waves of the same frequency. We will come back to phasors later in the CD. The radian. In theoretical discussions about power systems, the radian is sometimes a more meaningful and convenient way of expressing the measure of angle, and so we will define the radian. A radian is the measure of an angle with its vertex at the center of a circle and with an intercepted arc on the circle equal in length to the radius of the circle. The ratio of the circumference to the radius is 2 pi to 1. Therefore, the circumference of a circle in terms of its radius is given by the formula c equals 2 pi r. This means that a length of 2 pi radius may be laid along the circumference of the circle, regardless of the length of the radius of the circle chosen. Therefore, we can see that radian measure is independent of the radius of the circle. Also, 1 complete rotation is equal to 2 pi radians. If we want to equate degrees to radians, we can now say that 360 degrees is equivalent to 2 pi radians. Pi radians equals 180 degrees. Since our sine wave can be thought of as the representation of a circle over time, this relationship can be applied to our sine wave. Angular frequency. As stated earlier, 1 cycle is equal to 360 degrees, and the period corresponds to the time it takes for the waveform to go through 360 degrees. Omega is the angular frequency, which is given by the equation 2 times pi radians times the frequency. The resultant angular velocity, or omega, is in units of radians per second. A sinusoid is a waveform whose instantaneous magnitude at any angle can be calculated using the equation VI equals VP sine omega t plus theta, where t is the period, Vp is the peak amplitude of the waveform, omega is the angular frequency, which is given by the formula 2 times pi times the frequency f, and theta is the displacement or shift of the waveform from a reference point. As an example, let's calculate the voltage at 90 degrees for a sine wave with a frequency of 60 Hz, a peak amplitude of 10 volts, and a 0-degree phase displacement. Therefore, the instantaneous voltage at 90 degrees is 10 volts. Scalars, vectors, and phasors. Many quantities we deal with can be described by their magnitude, for example, length, temperature, and number. Magnitude is known as a scalar quantity. Other quantities, such as force, require both a magnitude and a direction to be described accurately. These quantities are known as vectors. What are phasors? A phasor is the representation of one or more waveforms of the same frequency. A phasor will have a length and an angle. The length of the vector represents magnitude, while the angle of the vector represents the phase angle of that waveform relative to another or to a time reference of 0. For a given load, we can use a phasor to represent the applied sinusoidal voltage V and its phase angle with respect to the load current, I. This is a graph of time versus amplitude domain for the applied voltage and current of the load over time. For a load that is purely resistive, we could draw a vector along the positive x-axis. The voltage, Vp, isn't a vector quantity, but is represented in this manner in order to assign an angle between the voltage and current. The key is to note that the phase difference between the voltage and current is constant and will be expressed. The direction is arbitrary. For the pure resistive load, the voltage and current will be in phase. This is represented as an arrow in the positive x direction, indicating that the voltage and current are in phase. If we were to try to describe the relationship between the applied voltage and resulting current, the current could lead or lag the voltage. A vector and angle is used to represent the applied sinusoidal voltage and its phase relationship to the current. Here is an example of a 135-degree phase shift. Note that if the reference waveform is considered to be 0 degrees, and the second waveform is phase shifted in the counterclockwise direction by 135 degrees, this would be considered a positive phase shift of 135 degrees. As stated earlier, the magnitude of a sinusoidal voltage is given by the equation VI equals Vp sine omega t plus theta. This formula can be represented as VI equals Vp at angle theta, where angle theta is the phase angle between this voltage and another sinusoidal waveform of the same frequency, for instance the current. Single-phase generators are commonly used as a source of portable or standby power in residential and small business applications. Alternating current in the form of 3 sine waves displaced by 120 electrical degrees is the most efficient form in which electrical power can be transported from the generator to where it is needed. Therefore, power in this form is delivered to large industrial and commercial users. 3-phase alternating current, or 3-phase power, is the name given to power in this form. Let's see how we can modify our single-phase generator to produce 3-phase AC power. Imagine for the moment that we took the stator poles from 3 single-phase generators, labeled them windings A, B, C, and positioned them to create the outer cylinder walls of a generator. The poles would be positioned such that the pole pairs are directly opposite each other, and planes running through any 2 pairs of poles will intersect at an angle of 120 degrees. This arrangement of poles forms the stator of a 2-pole 3-phase generator. It is called a 2-pole generator because the stator has 2 electromagnetic poles per phase. One side of the windings from each pair of poles is connected together, while the other side is connected to our 3-phase load. Let's plot a graph of the voltage, which appears across each of our load resistors against time as the exciter rotates through 1 revolution. We will see the waveform shown. As the exciter rotates, the voltage induced in each pair of stator windings will be displaced by 120 electrical degrees from the other 2, corresponding to the physical angular position of the stator windings. The resulting output is the desired 3 sine waves of equal amplitude, but with a 120-degree phase shift between them as shown. 3-phase phasors. We know that our generator produces 3-phase power for the power system, and so we can represent our generator's 3-phase AC output as follows. The 3 output voltages, A, B, and C, are of the same amplitude, and will therefore be represented by three vectors of the same length. The 120-degree phase displacement of the output voltages can be represented by joining the vectors at one end and having an angle of 120 degrees between each vector as shown. An output phase sequence of ABC can be represented by the labeling and the convention that positive sequence currents rotate in a counterclockwise direction. The rotation of the vectors, phase A, B, and C, can be seen here. The vectors are rotating counterclockwise. Symmetrical components. The theory of symmetrical components goes well beyond the scope of this course. The intent of this next section is to serve as an introduction to the concepts of symmetrical components, so that the student can better understand how modern microprocessor relays operate. Symmetrical and non-symmetrical systems. In the world of protection, we talk about symmetrical and non-symmetrical systems in addition to symmetrical components. A system is said to be symmetrical if it has only positive sequence currents. All three current vectors are of equal amplitude. All three voltage phase vectors are of equal amplitude. The phase shift between either the current or voltage vector is equal to 120 degrees. If one or more of these conditions is not met, the system is said to be non-symmetrical or unbalanced. Under normal operating conditions, an electrical power system is considered to be symmetrical from the generator to the load. When a fault or unbalanced condition occurs, such as a phase to ground or open conductor fault, the system is said to be unbalanced or non-symmetrical. Symmetrical components is the name given to a methodology developed in 1913 by Charles L. Fortescue. Using this tool, the line-to-neutral or line-to-ground voltage and current phasors of a non-symmetrical system can be calculated. Additionally, most microprocessor-based relays operate on symmetrical component quantities, and so it is important to maintain a good understanding of its fundamentals. According to Fortescue's methodology, a three-phase system has three sets of components: positive, negative, and zero for both current and voltage. The three are said to be independent of each other. The set on the left would represent the positive sequence current or voltage with a phase rotation of ABC. It consists of a balanced set where each phasor is of equal magnitude, displaced 120 degrees apart, and rotating in a counterclockwise direction. The set on the right-hand side is also a balanced set of phasors. The rotation sequence for this phase is ACB, making it negative sequence. The set of phasors in the middle have the same magnitude and are in phase with each other. However, since there is no rotation sequence for these phasors, they are called zero sequence. In a balanced or symmetrical system, the following exists. Positive sequence current flowing in the symmetrical or balanced network produces only positive sequence voltage drops, no negative or zero sequence drops. Negative sequence current flowing in the balanced network produces only negative sequence voltage drops, no positive or zero sequence drops. Zero sequence current flowing in the balanced network produces only zero sequence voltage drops, no positive or negative sequence drops. This is not true for any unbalanced or non-symmetrical point. Positive or negative sequence current flowing in an unbalanced system produces positive, negative, and maybe zero sequence voltage drops. Zero sequence current flowing in an unbalanced system produces all three, positive, negative, and zero sequence voltage drops. Before proceeding further, let's summarize. Under a no-fault condition, the power system is considered to be for the most part a symmetrical system, and therefore only positive sequence currents and voltages exist. At the time of a fault, positive, negative, and zero sequence currents and voltages exist. Using real-world fault voltage and current information, along with Fortescue's formulas, all positive, negative, and zero sequence currents can be calculated. The protective relay uses these formulas and real-world current and/or voltage data as the input to protective elements. In order to understand Fortescue's formulas, we must first understand the A and A² operators. The A operator. Like J operator in the complex plane which shifts a vector by an angle 90 degrees counterclockwise, the A operator shifts a vector by an angle 120 degrees counterclockwise, whereas the a squared operator shifts the vector by 240 degrees counterclockwise. Let's see how Fortescue's formulas work under a real-world fault condition. This sample of waveform data was captured by a GE Multilin SR760 feeder management relay. Sample 1's data is prior to the fault, while Sample 2's data is during the fault. Since we know the values of IA, IB, and IC, we will use the displayed equations to calculate the sequence current quantities at Sample 1 and at Sample 2 respectively. Once we have calculated the sequence components, the unbalanced currents of phase A will be recalculated using the displayed formulas to verify the results. Under normal conditions, power is being generated and distributed as described earlier. According to Fortescue, a balanced or symmetrical system only possesses positive sequence currents and voltages. Using his formulas, the positive, zero, and negative sequence currents can be calculated. Zero sequence uses the formula IA plus IB plus IC divided by 3. In this situation, we will use vector addition to determine the values. The formula calls for the addition of all 3 vectors, so by adding the 3, we can see that they cancel each other out, resulting in a zero sequence of 0 amps. Positive sequence uses the formula IA plus AIB plus A squared IC. We notice that phase B has an A operator applied, which will rotate the vector 120 degrees counterclockwise, lining it up with phase A. Since the equation calls for these to be added, we will place the adjusted phase B above phase A. Phase C has an A squared operator acting on it, which rotates the phasor 240 degrees, also aligning it with phase A. Again, since these vectors are to be added, we will place phase C above phase B. The formula then calls for these 3 phases combined to be divided by 3. Since the 3 are all of the same magnitude, the division will result in the positive sequence equaling 300 amps. Negative sequence uses the formula IA plus A squared IB plus AIC. We notice that phase B has an A squared operator acting on it. This results in phase B rotating 240 degrees and ending up on phase C's position. Phase C has an A operator applied, causing that vector to rotate 120 degrees, ending on phase B's old position. Now that the 3 positions are determined, we can complete their addition. By adding phase B and C to A, we end up with a negative sequence of 0 amps. As predicted by Fortescue, only positive current exists. Now a fault occurs on phase A. At the time of the fault, the GE Multilin SR760 feeder management relay measured the currents as shown. According to Fortescue at the time of the fault, positive, negative, and 0 sequence currents will exist and can be calculated. The relay determined that phase A now has a magnitude of 900 amps, while phase B and C remained at 300. Using this information, the sequences can now be calculated. The positive sequence formula has an A operator acting on phase B. This causes phase B to be shifted 120 degrees, placing it in line with phase A. Phase C has an A squared operator acting on it, resulting in a phase rotation of 240 degrees, and again lining it up with phase A. These 3 vectors can now be added, resulting in a magnitude of 1500 amps. They are then divided by 3, leaving a positive sequence equaling 500 amps. The negative sequence formula has an A operator on phase C and an A squared operator on phase B. After phase B is rotated 240 degrees, and phase C is rotated 120 degrees, the final position of these phases are known. Adding the 3 vectors reveals that phases B and C combined equate to 1/3 of phase A, however, pointing in the negative direction, requiring them to be subtracted. Given that phase A is 900 amps, subtracting 1/3 would result in 600 amps. After the 3 phases are combined, the formula calls for them to be divided by 3, resulting in the negative sequence equaling 200 amps. 0 sequence calculation requires all 3 phases to be added without the use of the A operator. Phase A, again, is 900 amps, and combining the vectors for B and C, we determine that they again equate to negative 1/3 of phase A. Adding the three together results in 600 amps, which is once again divided by 3, resulting in the zero sequence equaling 200 amps. To verify our calculations, we can use the predetermined positive, negative, and zero sequence current values to recalculate the actual current that should have been measured on phase A at the time of the fault. IA is equal to the positive sequence current plus the negative sequence current plus the zero sequence current. Our calculations determined that the positive sequence is equal to 500 amps, negative sequence is equal to 200 amps, and zero sequence is equal to 200 amps. The result of adding the three together is 900 amps, which was the actual current measured on phase A at the time of the fault according to the waveform captured on the GE Multilin SR760. Modern microprocessor-based protective relays use symmetrical components to calculate the positive, zero, and negative currents and voltages from the signals provided by the CTs and PTs. These quantities are then used by the protective elements within the relay.